So what we're looking at today is we're going to start by looking at two branches of a car rental company. So we've got the car rental company at Dandenong, and we have a car rental company and we'll go for Geelong. So this is Dandenong, Geelong. Now, on any 1 week, if someone rents a car from Dandenong, 40% of those people will return the car back to Dandenong. The other 60%, they end up going to Geelong. In Geelong, however, 50% of the cars rented in Geelong are returned in Geelong. The other 50% go to Dandenong, and they are returned to Dandenong. What we can do is we can represent this situation with a matrice. All right. So what we need to do is we need to set up this one here is going to be an example of a 2x2 transition matrix. So what I'm going to do is I'm going to set up a 2x2, and I'm going to describe it by saying, okay, rented in Dandenong, rented in Geelong. So these are the places that the car was rented in. And then here are going to be D and G for this is where they were returned. So my question for you is, looking at the diagram that I've got here, as a decimal number, what number would I put in here for rented in Dandenong and returned to Dandenong? All right, so cars rented in Dandenong and returned to Dandenong is 40%. So 40% as a decimal. And the number of cars rented in Dandenong but returned to Geelong. What's going to happen? What's the number down the bottom here going to be?
I can't see what's the number in red.
It is 60.
0.6.
Yep, thank you. Now, if we look at the rented in Geelong and returned to Dandenong, we've got this 50 here, so that's going to be 0.5. And then rented in Geelong, returned to Geelong is also 0.5. What I can do is I can use this transition matrix to quickly work out if I have X number of cars in Dandenong and Y number of cars in Geelong, at the end of the week, how many will I have in each place? So for example, if I started with let's just go some nice easy numbers. we start with a connection diagram, but we turn it straight into a matrix and then forget the original diagram. So if I start with 100 cars in Dandenong and 100 cars in Geelong, I'm going to need a matrix to represent the number of cars in, so this is number of cars. So that's going to be D and G. So it's just going to be 100 and 100. So what sort of matrix have I got? What sort of matrix is this up here? What's the order of the matrix? Yeah, it's a 2 by 2. And what about this matrix here? Down the bottom here. So, if I call this matrix A, and I call this matrix B, and I multiply matrix B times matrix A, what size matrix am I going to get in return? It's not going to be a 2 by 2 because it's going to be a 1 by 2. No, that's all. I've got two values here, two columns, 2 rows, and this is 1 column, 1 row. That's 100, not 3, not 100. It's 100 and 100.
Got it, my bad.
Okay. So it's a 2 by 2. So they match. That's cool, but it's going to create a 1 by 2 matrix in return. So what that means is we need to break out Mr. Kaz. Right. So, main. Oh, that was just me with my other kids. So, we're going to define some matrices for us. So, keyboard, math to need a square matrix. So, this is going to be 0.4, 0.5, 0.6, and 0.5. We're going to store that in matrix A, and then we need to set up a simple 100, 100, and we're going to store that in B. Now, we do B times A. Someone's made a mistake somewhere. It's not a 2 by 2, it's a 2 by 1. Remember, rows first, then columns. So, So we're going to do a 2 by 2 times a 2 by 1, which will create a 2 by 1, which is the matrix that I have here. A times B, 90 and 110. So, if at the start of the week there are 100 cars in each place, because of the way the rental system works, over time, at the end of that first week, you're only going to have 90 cars in Dandenong and 110 cars in Geelong. That's after week 1. Well, what happens if I keep repeating this process? A times ANS. Answer. At the second week, 3rd, 4th, 5th, 6th. Alright, so I'm going to take that off of standard. Now, obviously, the change here isn't that dramatic, but as you can see, it bounces between 91 and 109. But it stays the same. It suddenly becomes stable again. Which means that occasionally, how many cars are they going to need to manually make a special trip from Geelong back to Dandenong to return the cars? If you're supposed to have 100 in both places, how many cars would need to make a special trip? Right? Because you don't need, if you take 9 back manually, you'll eventually get to 100 and 100 because of the way this equilibrium, this balancing point works out. So, if, for example, we started with different numbers, say we had 80 cars in Geelong and 120 cars in Dandenong, and we run this experiment again. Look what happens to the general balance of the cars. If you were to round these to no decimal places, approximately how many cars are you looking at in each place? How many cars, if you were to round these off, would be your balancing point for the number of cars? So you have 109 cars where, though? G. Yeah, G for Geelong. So you'd have 109 cars in Geelong and 91 in Dandenong. So the idea is that by running through a repetition like this, we can figure out at what point a transition matrix and the state of that matrix reaches what is called a balancing point, where the numbers basically never change week on week. So I could ramp this up and I could go to the thousands. So we can talk about, 1,250 cars and 650. And I could run this experiment. And what you'll notice is that it converges on a set of values pretty darn quickly. And that means that every time I run this experiment, what's happening to the fundamental numbers? Are they changing at all? I mean, all I'm doing is just putting more and more decimal places onto my question. But what it's showing is that it's reached a balancing point. So what we have is a state matrix. So these are some special words that go on that would happen at the start. So this matrix that I've got up here, which talks about how the numbers change each week. So this here is called a transition matrix. And this matrix here is called a state matrix. If, for example, I am doing a problem like this and I'm doing it repeatedly, and this is my first measurement, then this is also called the initial state matrix. Now, the transition matrix is generally labeled as being T, and a state matrix is generally labeled as being S, where there's a little number down the bottom there that represents the number of times a particular state has been calculated. So the initial state matrix, how many times have I done the transition matrix to it? If it's the initial state matrix, how many times have I multiplied the transition matrix into it? Nothing. So the initial state matrix is S0. Not so. I'll label it like that, S0. If I was to do the experiment, if I was to do this experiment once, then I would get, so what did it come out as? It came out as 90 and 110 the first time I did it. That would be S1. Because I've multiplied, I have done this. So I've done T times S one time. If I was to repeat it again, it would be 91 and 109. And that would be S2. If I did the calculation again, we'd call it S3. And so on and so on and so on. So, if you guys think back to financial maths, we had this wonderful thing called a recurrence relation, where we could talk about the pattern and use it to describe what's happening. So we can actually describe what's going on here as a recurrence relationship. If S0 equals the initial matrix, then S of n plus 1 is equal to the transition matrix times the current state matrix. And now all of the recurrence relationship stuff that we did at the start of financial maths now suddenly comes into it, because this is a recurrence relationship, and what I can now do is I can actually use it to make quick predictions. This relationship is true. However, what I can also go is after n steps, I can calculate it as Sn is also equal to t to the power of n times s of 0. So, that's all I'm going to talk about today, because I want to leave some for when we get back to the end of when we get back to school on Wednesday. So I'm going to stop the recording here.